So hello and welcome everybody to a new seminar organized by IBiDat. Today we have Diego Perino with us, who is the director of Telefonica Research. He leads a team of researchers in machine learning, deep learning, human-computer interaction, privacy and security, networks and systems, quite a good team. He works at the boundaries of research and innovation. So he takes advance of the state-of-the-art in technology areas relevant to business and ICT, and he ensures the successful exploitation of this research output in the company. So as you can see, he is involved in the research and innovation communities. He's here to tell us about their experience in the research and the deployment of artificial intelligence techniques in a large technology company. So when you are ready, Diego, you can start. You are mute.
Unmute myself.
Okay.
And let's try the share screen again. Okay.
Now.
Can you see the screen now? Okay.
Yes.
So thank Patricia for the introduction. Thanks for inviting me. It's a pleasure to be here. And next time I was telling Patricia before, I'll try to be in person, hopefully. But it's still great to be able to be here with you. And the talk, I'm going to cover some of the work we are doing in application of artificial intelligence towards, I would say, telco industry, as well as some challenges in terms of privacy and what can we do to preserve privacy in this context. The work covers a lot of work we do in Telefonica research, but also try to give a bit of a broader view and not only the one about Telefonica itself. And so just a disclaimer before to start, by artificial intelligence here, I'm probably abusing a bit of the term. I refers to machine learning, deep learning model mostly, or statistical tools. I know that that's a partial view of what artificial intelligence is, but I just use AI to make it short and don't repeat 3 times machine learning, deep learning, etc. all the time. And yeah, also please feel free to interrupt me anytime for any question, because I'm going to cover different topics throughout the talk. So probably not forget the question. Feel free just to drop the question anytime. Okay, so here is the not so short let's say agenda for today. I'll give you a little bit of how I see artificial intelligence networks in a broader sense, meaning, and cover what artificial intelligence can do for network and what network can do actually for artificial intelligence, and then cover some of the challenges in terms of privacy and security and how we could deal with that, and try to go through this journey and show some lessons we learned while doing research and innovation in this area together, also collaboration with other teams. I was saying, we have to thank my collaborators. This talk won't be possible without them. You will see references across the presentation, and thanks to all of those. And also thanks to funding, which again, without that, this talk won't be possible. But before to that, you probably know us already, but still, let me give a few words on what we do in Telefonica. We basically do 2 main things. Telefonica research, sorry, and Telefonica's brother. What we do is we work in research, so more on academic style kind of research, where we advance state of the art, we publish, and we organize events, we go to conferences. We work collaboratively and openly with other institutions, for instance, in European funded project or national funded project. Looking forward to collaborate more with you, though we already work with some of you, and we have been working with some of you. And then the second thing we do is you actually impact Telefonica throughout this research work that we have done, impacting the Telefonica business in different ways, collaboration with different teams. So that's the double role we have at Telefonica. We are based both in Barcelona and Madrid. You probably are familiar with these places. And as Patricia was saying earlier, the team covers a broad spectrum of topics, but that can sort of be categorized in 4 areas, which are network and systems, security and privacy, machine learning, deep learning, and human-computer interaction. People have expertise in these fields, but the team is a flat team, and all work it's cross areas. So many of the projects, especially the ones I'm going to cover today, cover at least 3, but if not all of the 4 actually area of the team. And yeah, all these areas are also very relevant to Telefonica businesses, so that's we can leverage this kind of work internally. Okay, and yeah, I mean, we follow an open collaboration model where we work with other institutions. So happy to discuss offline to other potential collaboration that we can have in future. Now, I want to start, like I always start with this picture when I talk about telco networks, because very often, especially when you finish your school and you have this image of, okay, the network is a nice graph with edges and a very nice set of protocol which allow everything to be smooth and go very well. But as you all know very well, things are not that easy. And even the telco network is actually today way more complex. Not only a telco network, but it's many more things. So things starts already. If you see in the left-hand side of these slides, you have the user devices, and these are very broad. There are many IoT devices in the home, outside the home, connected via wireless, connected via cellular. You have the gateways at home, you have the home devices, you have your phones, you have your laptop. So all of these devices per se, it's already a very complex work. It's complex work. It's managed by a set of protocols, set of rules. There are several companies operating in this world. There are telcos, there are vendors of IoTs, service providers, even just within the home, even before the home or in the user side, before reaching the internet, you already have a complex set of protocols entities interplaying with that. Then you reach the access, which can be fixed or mobile. Mobile that's today accounts for 2, 3, 4, 5G, just to give to make things simpler. Access can be fiber, DSL, okay, mostly fiber these days. And again, there is a different set of protocols, perhaps a different set of companies managing this, and even within the same company, very often there are different teams managing this, which makes they talk or not together, which makes things more complex. Then we have not even reached the actual network, let's say. There you have multiple ISP, multiple MNOs, which then interconnect with the core network, which again, different protocol, different teams, different entities. And then there are the platforms, things to IoT platform, roaming platforms, video platforms, CDN. So there are so many actors here. What I hope I was trying to make the point here is that even within a single company, there are multiple teams, multiple entities, multiple networks, multiple protocols, and so this is a kind of very complex ecosystem. So what can AI can actually, let's say, help here. Actually, or the network itself can help AI in different ways to, I would say, simplify or the role and the work of operation, or the network can simplify and help the role of AI, as I'm going to tell you a little bit later, and in this very complex ecosystem. And I always like to categorize the interaction between networks and AI in two areas. So what can intelligence do for networks? And so you saw there is a lot of complex ecosystem starting from the left-hand side. So the user, the home, the devices. There is a lot of machine learning, deep learning models that work in these IoT devices, or things for your home devices, where you have artificial intelligence for speaking to show images. Or so there's many of intelligence there based on AI techniques. It can help in network planning. So, how do I have to plan my network, spotting trends beyond what's based on domain knowledge. It definitely could help network operation to provide QAE to quality experience to the end user by simplifying the life of operation and again, detecting anomalies or helping them to detect trends and prediction. Network management, I hear, anomaly detection, orchestration, forecast. So there are many ways in this complex ecosystem where intelligence can help and improve what is there out there. I would say, I like to say that it's more like it complements, it won't replace, because we'll see later AI has also some limitation already in that. But so this is one side of the coin. But on the other side of the coin, I will say that intelligence can benefit for network, because the network is a distributed system. So, and very often because of the size of the data or because of privacy constraint, the network can be used as so you can do some distributed work on intelligence, for instance, distributed training, or leverage the network for getting closer to the user. I'm going to give an example later on. So actually here the network can help the AI and not the other way around. Again, I was mentioning already security and privacy. If you think of federated distributed learning, you don't move the data, which makes, help at least improving the privacy for the user, or AI application at the edge where, you are very delay sensitive application, boundary language application where you really need to be close to the user to provide bandwidth. So I see these two ways. I'll try to give you some example of those in the next of the talk, and of course there are more of the example. Okay, I'm going to give you now two examples of the way we apply artificial intelligence to help network. I will give you into the details of two, but before that, I want to give you more examples that I don't really have time to cover today in details, but happy to talk more offline. And this is not, only work we are doing, but it's work that it's done also in the community. So there is a lot of, I was mentioning a lot of IoT devices which are growing. I don't have to tell you more about that. And many of them actually are working in roaming. And that's a very interesting ecosystem because here you have the IoT vendors, and very often you have the mobile network operator, the fixed network operator, and when they are roaming, very often you also have the interconnection and even the visitor net. So it's a very, you see here there are a lot of entities involved, and very often these devices are managed by an IoT platform, which is yet another entity. So here, what these different entities are very often interested in characterize, let's say, the trending of the device, the volume of traffic, the activity of the traffic, the signaling. So do some prediction and characterization. That's one of the things that typically these entities are interested in. Or detect anomalies. This is a very complex ecosystem. Just looking at one side of one source of data, it's very hard to get detect anomalies, and very often this is based on rule or strict set of rules. So here again, machine learning can help that. And in this context, there has been several work applying several techniques, machine learning, deep learning, time series clustering, and that have been applied to this era, I would say, successfully. Also, I always want to say that very often people think, oh, let's apply AI. I'm going to apply a super complex deep learning model. That's not the way I see it. It's actually very often, I will talk later on, simple model works well. There are other issues that you have to deal with when applying this technique to network data. Another example where there is a lot of interest in these AI techniques, the core network. And again, there are these two sort of two kind of example. One is to get in trends, so forecasting traffic, forecasting peaks, so that actually you can plan and or react dynamically without having to strictly set rules. And or detect anomalies. Again, very often there are unpredictable anomalies. It's good to detect them or predict them, right before the problem becomes to use it. And here, very often, machine learning model or deep learning model can help and have been shown to work and help in this case. Another example is slightly different. It's about the quality of experience of video. When you are telco network, very often you don't have access to the end user device, to the video, and so you want to be able to understand whether your user is getting the right quality. But there are only from network data. So there are some models that we and others have been deploying to predict or detect what the quality is just from the network data without having to tap into the application, of course, after having some sample of the quality of the application. And this stuff's shown to be fairly accurate, though not that easy because you need a lot of it. So these are some example of use cases where intelligence can help network. And again, there was a lot of work have been done in the research community, and some of those are actually being applied also more into production. Now I'm going to give a bit deeper view on two use cases we have been working on where AI can help network. And one of them is about unconnected remote communities. So Telefonica Innovation developed a project which is called Internet para Todos in Latin America. And it's been working running for a few years now. And the goal of the project is basically to provide infrastructure that different MNOs can leverage in remote areas. When I say remote, really remote. These areas are very often tens of even some hundreds of kilometers away from the main road. They are on the mountain, on the coast, even in the rainforest. And they're mostly 2-3G sites. Some of them are 4G. There are different power supplies. It can be solar panels, some have power grid, many of them rely on batteries. And then they interconnect with the core with third-party backhaul. It can be radio, satellite, fiber. And so as you can imagine here, given the situation, the geographical location of these sites and what they harm, it's very hard to do operation in this area. And especially when a problem occurs, it is very costly to go and fix one of these problems, because you have to send a technician that has to do a long way to get there, get the right tools to fix it. So what the operation teams try to do in these sites is, first of all, to try to solve the issues from remote. And then only when the problem is persistent, they send a technician. They try to batch together team fixes in the same route so that people can fix that. So what the team has developed here in Telefonica is they have put together this data lake, I would call it. It's more like a system to collect information from the site, because in this, as you could imagine, given the complexity of this scenario, you really need to have a lot of data and take data-driven solution. And so they have this alarm collector and failure collector when they clean the alarms and get it from the different part of the network. But what's interesting is that on the top of this data, they extended the OSS to be able to run some analytics and extract values from this data that can help the operation in different ways. For instance, of course, they have from the more traditional monitoring dashboards where you see trending, some diagnostic dashboard where you say, okay, now you could do that, or even what they call the rural bot, which basically tells technicians where to go and what to go. So on the top of those, actually, you can plug models. Can be a statistical model, can be a machine learning model to fix. So it's very important in these kind of areas to have this kind of data-driven approach, given the complexity of this operation. Now, what we look at specifically in this scenario, we look at failures. We look at 5-month data failures in this scenario. So failures are mostly related to backup saturation or battery outages. And I don't want to spend too much time in explaining you this graph, but what I want you to take away from this is that the failures are very short in time. Most of the failure lasts less than 1 hour and get fixed by themselves without any intervention. And this is because, again, it's backup saturation, so it depends on the traffic. Battery outages, sometimes the power grid goes off, and then for a while there is no power. Sometimes there is rain, and when rain comes, there's a problem with solar panel. So there are a lot of problems that comes and get fixed by themselves. And the interfailure time is very short. Sometimes there is failure goes up, there is a failure, and then it goes again. Things get fixed, and then some of them. What is interesting, it's only 1% of the failures are actually persistent, and it really require intervention of a technician. And then so the question that we're working with the operation here was like, okay, so how can we predict if I have to send a technician or not, and when should I send a technician? Because of course, you could wait long enough to make sure, okay, now the failure is long enough, it's time to send a technician. But of course, when you wait this time to send a technician, then you're losing revenues and you're having a cost because you're losing customers. Actually, there's a lot of impatience in these areas. So you will need to find a trade-off, but so how can we predict or say after a short time or the shortest time possible that a failure is going to be permanent and I really need to send a technician to fix the problem? And here, what is interesting, so we work on this problem and we and start analyzing different solutions for different models. We looked at machine learning models, we looked at deep learning models, and also, of course, when working in this context, people were really interested about the cost of the solution, and can we reduce the cost, and can we improve the effectiveness, the quality for our user. But talking with the person, they were not really caring about precision, recall, or typical metrics that you work with in machine learning or deep learning tools. So we had to design a specific cost function, which actually depends on the cost and not on the monetary cost, and not on the precision and recall, which are traditional metrics we are more familiar with as machine learning. So there was this interesting interaction between network engineering and data science. And so what we end up showing in this work, which is actually published at Mobicom, you find the reference in the paper here, so you can have a look at that more in details. That what we show is that, of course, this failure are temporal. You don't really need to send the technician a lot of time, and you really need this sort of control and predictive mechanism. And these mechanisms could actually reduce the cost from 5 to 20% with respect to more knowledge-based rule or fixed time waiting of a given amount of time. And also, what was interesting in these specific projects is that we figured out that the design of the machine learning model not only allow to apply the model itself, but it also helped to define heuristics, which works very, very well, and that we were not aware of this potential heuristic before to do the analysis and the work. which is very interesting. And also, second thing is that we also try deep learning models, and actually basic machine learning model like XGBoost works fairly well in this context, or even heuristic derived from this analysis can be applied. So now this was one example of AI helping operation in a very peculiar context. I want to give you another example that we have been working with. It's about the video classification here. The problem here was, well, you all know what 360 video are, I think, more or less. And these are more demanding in terms of bandwidth and latency because of the nature of the flows. And it's very important then for ISP and MNO to be able to, say, predict, identify whether sessions that are going on are video or 360 video flow for planning or for reacting to anomalies and so on. Now, the question that was posed to us and we posed to us was, can we actually distinguish between 360 video and flows and regular flows? And what is interesting in this case is that, of course, you don't have, especially when you are at the MNO ISP level, you don't have very low level statistic. You don't have packet level statistic. You have very aggregated flow level statistic. Can we design a tool which enable us to distinguish between 360 flow and regular video flow so that we can actually do some work on that? And so it turned out that the problem, especially when working at flow level, it's more complex than what we thought. And there were not simple heuristic on that. So we work at, trying to define a solution based on machine learning and deep learning. And especially was interesting because what we did was trying to move from something which works at packet level, that can, for instance, be applied on a LAN or in a small scale scenario. And then, but that won't be able to be applied on an MNO or on an ISP because that you don't have that kind of statistic. And can we extend that to flow level? And actually, we showed that that is possible and keeping a very high accuracy of like 93 to 94% with, and that could be done also in almost real time, like with 1 minute of traffic, I would say 30 seconds to 1 minute of traffic and counting a few flows of the session. And actually, we even tested with under control environment in an MNO and showing that even there, where statistics are very few, that could be possible to achieve like 92 to 94 accuracy with 1 or 2 flows of the session. And so there are more details on the paper that I'm pointing here, which was not started this year. Please have a look for interesting. And also one lesson learned that we learned here is again, a simple machine learning model was able to perform as good as more fancy deep learning model because of the nature of the data that's available in this specific context. Now, I just wanted to summarize a bit, some of the lessons learned and challenges that we see when applying AI supporting networks. So one typical problem you have when you deal with space is the lack of ground truth, because okay, there are some ticketing system, but this ticketing system reports only measured issues, and there is not much information about anomalies. There is not much information about ground truth. Even in the QE case, there is not really much information about the QE. So you really need to build this ground truth and work very closely with the operation to check the issue, and very often work in a supervised way and then have a closed loop with the operation. But that's that's a major problem when you deal with the networking problem, which very often when you work in other area where AI has been applied, like speech, images, you sort of have a ground truth which is well established, and that's actually very interesting when working with data scientists, networking people. This interaction that data scientists say, oh, but where is the ground truth? Why you don't have the ground truth? How do you? So it's very interesting, this kind of interaction. And also, as I'm talking about this interaction, what is also very interesting is that these two words talks different languages. Data scientists talk about precision recalls, algorithm, while network engineers very often talk about protocols, incidents, issues, packets. So it's very, very important to make sure that whatever, I was giving the example of the monetary cost before, whenever you work in this context, you define a metric which is useful and explainable and easy to understand by network engineers. And also when you point out a problem or an anomaly, or make sure that you are explaining that in a way that is useful to them without having them to dig into data because there's not explanation. Also, it's very important, and here what is actually more important in this context is, at least from what we saw, of course, it's very important. We're now at the stage where probably after trying different models, you can still improve a lot the algorithm that exists, but very often the basic model work fairly okay, though they need to be extended. But what actually is more hard and important is to represent the input data and the output, and having a proper monitoring system that provides the good data. And also, because of the lack of ground truth, it's very you have to interact a lot with the operation, but these are busy teams that spend a lot of their time fixing the network, so you don't have much time to interact with them. When we talk about network problem, very often it's very unbalanced, more unbalanced than the usual problem. The data is very input, and very often the data is noise. Again, this is important of cleaning data and preparing data. Maybe I'm saying a naive thing here, but it's very important, and I would say in this context more than all. Another important is, again, having this data monitoring infrastructure, the time scale, and the solution robustness. This is very important for operation, because whenever you talk, okay, we have a solution, especially we talk about security, you have a solution which works statistically, which is a machine learning model, but they then don't want to have statistics, because even if there is a percentage of failure or of wrong, even a few false positive or even false negative, might dramatically impact the infrastructure. So how can we make the solution that robust? And this is actually a challenge which is still very open when applying network AI to networks. And very often, again, you need to do some per vertical solution within a given infrastructure. Customers are different. You need to, sort of customize the models and the techniques. And very often, when you don't know how these are used. So, I mean, I think there has been, some application already on those. There are some very good results. I think there is, still some way to improve the usage of AI to networks, to get it more benefits, and some interesting research challenges ahead of that. Now, I want to touch a little bit on the, feel free to ask questions if you have any at this point, or I'll just continue. I don't know if there is any, or I'll go ahead then.
In the tab, there is no questions. I don't know if anyone wants to raise a question directly.
All right. So then I want now to move a little bit on what can network actually do for AI. And I want to talk about this application like AR, VR, 360, computer vision, autonomous driving, industrial IoT, video space. Many of those applications rely on some AI-based primitive, like mostly machine learning or deep learning inference. And these applications are very sensitive to what the network can provide them in terms of latency, bandwidth, and also resilience, meaning that they have to provide stable performance. Now, the question that we posed ourselves is like, we'll take at one of these metrics, which is mostly the latency, and say, do we really need to move all of these inference at the edge? So can I, or we just can stay in the cloud? So basically, so where is the bottleneck? I like to show again this picture of the complex network with different elements, different central entities, different edges. And where is the place where to run this function, and can the network and being close to the user help the machine learning and deep learning application? So what we did, we developed two applications, one based on one object detection, and the other one is speech recognition, which are based on some basic machine learning, well, actually some basic deep learning building blocks. And we look at the inference. So, and actually the first question we start is, so what is the bottleneck? Is the bottleneck the network, or is the bottleneck the computation? So what we observe here, I don't want to go too much into this, but here an experiment with a single CPU, a single core of the models that have been improved across the year. And well, inference and object detection used to be in the order of 15 seconds in the last models. And I think this has even been improved with the latest version of YOLO. It goes to second level, I would say, latency in terms of processing, which is still a bit far away from network latency, but still start getting close. But now, what if we start increasing the number of CPU? Then you get to sub-second level and got in the order of hundreds of milliseconds. But you can even get better if you start using some specific optimization in the libraries that you use. And there you get really, in the latest with just 12 CPU, and Tiny YOLO to 70 milliseconds, which gets very, very close to network latency, or in the same order, depending on where you have the function that runs. And here, what if you use a GPU? Then okay, then there you really get into the 30 milliseconds. There again, here we are really talking about network latency being comparable, if not higher, than the processing latency. And so then the network here can be the bottleneck. And so the network actually can help, or edge computing, or some of these tools can actually help AI to get better performance thanks to interaction with networks. But now, is this true all the time? What is the edge? Where is the place where it's sharp? And again, I want to show here the picture that there are very, very different edges of the network. It can be, some people think the edge is the home. Some people think the edge is the central office. Some people think that the edge is the peering point in the internet. Well, some people say, okay, I can just go to the cloud. So where is the edge? What is the right place to run this function? How can the network help here? So what we did, we have a testbed that we use to test the mobile application, which is based on traditional in-B central office, and then ISP data center, connection to the internet, and AWS. So different places where computation can run within the ISP or not. Very often the InnoD is collocated with the central office, at least in the edge deployment. But here we assume a scenario where it is not, so that you have a little bit one step further. And the question we asked ourselves, so depending on the application, what is the right place to run it, and can the network or the edge, let's say, provide benefits to applications? So we started with a simple, again, we focus here on latency. And we started with a simple application, which is an application to give and drive instruction to build something. In this case, what you want to build is a sandwich. And here's a breakdown of the processing delay versus the delivery delay. And we observe that the two are comparable at the sub-second level. Though this said, it doesn't really matter where you run it, you still meet the SLA, let's say, of this application, which is 600 milliseconds, because that's the typical QE per se. So the user is satisfied with that latency. So in this case, it doesn't really matter where you run the machine learning tool. Will obviously benefit. In this case, there's no really benefits from the network. Just run it into the data center, and all is good. But so this was done with CPU, by the way. But then there is not even need of a GPU because of the high latency that you have in processing. The high value that you can tolerate in terms of SLA. Now, but what if you're talking about an autonomous car case? So here we really need to use GPUs, and not only that, the processing really needs to happen at the first stop of the network. In this case, which was the InnoD. Now, in many places, the InnoD is collocated with the central office, so it can sit at the central office. But even traversing the network of the ISP and reaching the ISP data center, it cannot be enough to provide good performance to machines. So here you see that really this edge computing and the network itself can help and make sure that the SLA is met for this specific application. And then there are cases which are somehow intermediate, which is like this case of the voice over IP, where, okay, as long as the processing sits in the middle of the data, in the middle of the ISP network, mobile network operator network, it's still good enough for you to satisfy, but going out, it will not meet the SLA. And this was all done with 4G. Now with 5G, of course, network gets faster because the first stop it's faster than that. This was done with a 4G test. Now, what I want to stress here is that, okay, we are reaching a stage where the processing itself is not the bottleneck, and the network might become the bottleneck, and actually the network or the edge computing can help this AI-based application to meet their performance required. It's also what I want to stress is that actually there was some recent paper showing that even in the data center now, the bottlenecks within the data center can be a bottleneck because of how fast the processing became. Not all interactive application, not all application actually requires to run in the network. And this will, 5G will also make this more interesting. So you can point to this paper, and we're still working on this topic. Now, so I hope I convinced you that there is this interaction between AI and networks, which can be beneficial, though it's not fully explored and there is still some room there. But one thing where you talk about AI is that artificial intelligence per se, again, talking about machine learning and deep learning tools here, are also vulnerable. And there is a new attack surface that was not there when these tools were not available. And this attack surface can, detect some attacks there can, attack the membership or being able to identify who was there, reconstruct the data, infer properties. And in this case, user data or privacy might be compromised. And that's also the case when, when companies trying to share data to one of these given goals. Luckily, there are tools that somehow can help to limit this attack surface or prevent some of the attack. I'm listing here Federated Learning, trusted execution environments, our differential privacy techniques. And so we have been working in some of the tools, and I want to give you an example of two works that we have been doing in this context. Which one of those is Federated Learning as a service, and the other one is privacy preserving Federated Learning. So for those who are not familiar with Federated Learning, I'm going to give a very quick introduction of it. So Federated Learning, the goal is that basically you don't want to collect the data in a centralized place. You want to train the model without leaving the data on the user devices. And so the way this works is that the model is bootstrapped in a centralized server, probably with public knowledge data, so that you don't You don't need to collect any personal data, and then it's sent to each client. Each client personalizes the model based on its own local data. The model is sent back to the centralized server, and then there is an average that is done. Well, but there is an aggregation. The averaging is the typical, most typical application that is done there. And then the model is sent back to the client. And this, after a few iterations, it's been shown that it can reach very, very good performance, very close to the centralized model performance. There's been a lot of work in the space of federated learning, mostly so far in the context of mobile devices or IoT devices. But there's been also some hierarchical proposal clustering, etc. Now, what was missing there? We observed that all of these were sort of monolithic application. Basically, the model itself was done for application, but there is no solution which allows to do modeling across application or across entities, or across companies. How can we do that? And can we try to do that, making sure that we guarantee the privacy and manage the permission in a correct way when you have collaborative parties that are not from the same company? And can we take advantage of the topology of the network to have better functional convenience or limiting the privacy leakages? And can we do that as a service fashion? As today there are these as a service application for machine learning. Can we do that for free? And so what we propose is federated learning as a service, which actually meets the design goal that I just listed above. What it does, this tool, is provide a high-level API and SDK so that this can be used easily with people with limited knowledge of what federated learning is, or even no knowledge of what it is. Similar to what, again, other popular machine learning as a service tool do. It enables collaborative training across customer of different applications, uses simple API in a federated, secure, and privacy-preserving fashion. It also allows to do hierarchical construction of the model, as well as work in different kind of devices. Can work on phone, home devices, edge nodes. And here I want to give an example of few use cases. So the first example is, okay, an app. Probably Spotify, Instagram, not a good example, but an app that doesn't have the resources to develop its own federated learning system. So it can just use this service to do federated learning on its own application without having to really bother to deploy and develop and get the skills to be able to run this kind of tool. But then there is the second case. Okay, let's assume there are two apps with similar goal, for instance, images or music or videos, that want to build a model which is more powerful because you put together models of the different apps. We put together data, but can we do that in a fully privacy preserving way? So that's the second case that we are actually able to solve with this approach. Or yet another third use case is that two applications that wants to build a third use case, putting together data from different use cases. So for instance, a driving company who wants to put together with music companies to do recommendation, or a geographic company again with the music company. So these are the kind of use cases that we enable with federated learning as a service tool, and this is done in a simple way with a simple SDK and the API. So there is a paper that's been published last year. You can have a look at that, and we are still working on that. Now we built a proof of concept. We are deeply evaluating it, and we showed that actually. So in the previous paper, we showed that this is feasible, and actually the model that this extra as a service tool doesn't really impact the execution time memory, and the collaborative model actually improves the accuracy with respect to building a model alone. And yeah, again, we are still working on that, and we will come up with new results soon. Now, is federated learning the answer to all privacy problem? Well, no. It's been shown that though the data does not leave the user, still there are attacks that are possible. This is possible because of what can be observed from the gradients that are exchanged. And this is, typical example of model here is the attack model here is the honest but curious, where people do not mess up, the entities do not mess up with the protocol itself, but want to learn something from that. And there are, been shown that people can do, the data reconstruction attack, property inference attack, or membership inference attack, just looking at the gradients. Now, what we want to do, can we? Yeah.
Let me interrupt. There is a question from
Sure.
the audience, so I just read it. Is this tool usable for mobility analysis applications?
No. Actually, I think one of the use cases can be, for instance, in your home devices, where you can do that in a federated learning fashion. So there are very often in your home environment, you have different devices which belong to different companies that can do that, or there are some IoT companies, or even Telefonica enables to build, to have different applications running on a shared framework. So there it can run on those. It can also run on IoT devices. Now, what we have been prototyping, and you can see that in the paper for mobile phone, but the concept can be extended to more. Now, the code base, of course, needs to be different, but the concepts and the basic, the design can be the same. I don't know if that answers the question.
I guess so.
Okay.
So thank you for the question and for the reply. And there is also another question. So
Sure.
Miguel says, I assume that the global model would have many more observations than the global one. If that is the case, are the local observations weighted in order to give them more impact on the model than the local one?
Sorry, is it the global model would have more observation than the local one? Sorry.
Than the local one, yes.
So that's, yeah, so that's the, so that is the typical goal of what Federated Learning does, that putting together the data of multiple users, you get a better, more information than building an isolated local model. Now, and that without moving the data. Of course, you would have a similar performance if you get all the data in the same place, but we show that Federated Learning actually can do almost the same. Now, the thing is that when I apply the global model to my local data, would the local model perform still, a model based only on local data perform better? That really depends on the data sets. In some cases, yes, in some cases, no. Depends on how many samples you have locally. What's been shown very often that is done in some of these applications is that once you have the global model trained, you do some personalization on your local data. You still have enough information gathered from the global model, but you have it personalized for your local data, so that you have a better performance from your own local data, but you don't suffer from overfitting because you have trained the model with enough sample in a centralized model, with the centralized data. Let's say, even if it's not centralized, let's say with centralized knowledge gathered from all the users.
So thank you. I guess you can continue.
Okay. So yeah, the idea is so that can we prevent this attack of gradient to the gradient, so to attack the models? And the idea was, can we use trusted execution environment? So trusted execution environment, I think you're familiar with it, but it's a memory where you cannot really, as long as you trust the CPU, even if you run the OS or the application, you cannot look what's inside and what's happening inside. Now, the good thing, that's the good thing. The bad thing is that the memory size of this trusted space is very limited. For instance, 128 megabytes. So, can we use that to train Federated Learning model? But the problem is that very often deep learning models are way bigger than the TEs. So the answer is yes, and but that needs to be done with a specific design. And actually, what the design does here is basically do layer per layer training, where basically each layer is trained individually and then frozen and passed to the next layer. And this is done only trusting the TEs at the server and at the client. So let me explain you better. So you have the TEs at the server and the client. The dataset, the private dataset, sits within the client. So the public, you bootstrap the centralized model with public knowledge, and you send this public, this model to the clients. Now the public knowledge, it's public data, so there is no sensitive information there. So now in this case, then you have freeze the first layer, which are the one that usually are based on. It's good to base these on public knowledge or a base data set, and you start training the subsequent layer. And you start training the subsequent layer in the TEs. You have a secure channel talking to the TEs of the client, and then the H client in this TE train its own local layer, and then it's sent. Once it's from the private data, and once this is trained, it sends it back to the TE of the server, which does the aggregation. And then it sends the model back, which is frozen and stored in a secure way. And you proceed that way until convergence. So what we have shown that, and you can find more details in our Mobisis paper. So by the way, the code is available, so you can play with it. We observed that actually this approach, it's fully privacy preserved in the sense that there is the known attack, at least that we are aware of, were not able to be performed against this technique. The performance of the model is the same as if you would run it without the technique, with even less communication cost. There is, of course, a penalty in terms of system, but the penalty in terms of system between 10 to 20%, which makes it suitable for deployment. So the overhead is something that you can tolerate. And actually doing this layer-wise training, you can actually batch together multiple layers, use a single layer, so that makes it a good fit for cases where you have a heterogeneous environment with different sizes and different categories. Again, there is the code available, so for full reproducibility, and you can find more details in the paper. Just to sum up, so I hope I showed that there is this interaction between AI and networks that can be beneficial to both. So AI can help operation and security and privacy of complex future networks, including from IoT to access to core platform. Still, though there has been 20 years of research and a few years already now of deployment of AI within networks, is not a fully mature area, and there are still many challenges which open for future research. For instance, the interaction between network engineering and data science, the language and representation which is suitable for network data and networking problem. Well, this is very mature in other areas like speech, NLP, or video. That's not, that there is still a huge gap with what's done in network. But also, it's interesting that networks can help AI, for instance, in edge computing or distributed infrastructure, can enable some application to meet the ESLA because they get close to the user. You can distribute the training to provide privacy. Same time, whenever you talk about AI, there is an issue. AI can be attacked, can leak private information, and there are some emerging approaches that can somehow prevent. But this said, there is still a lot of work, interesting work to do that. With this, I conclude my presentation and be happy to discuss with you more and hopefully collaborate in future.
So thank you, Diego, for the nice presentation and the nice work that you are doing in this area. Now it's time for questions. So people, if you are not in side mode, you can just unmute and ask the question directly to Diego, or if not, I read the chat.
I have a question, Patricia, Alvaro.
Go.
Since nobody is asking, I will do that. Yeah, very interesting talk. Thank you, Diego. I was just wondering, in terms of AI and robust, secure and robust methods for this kind of, I wouldn't say all of them because maybe not all of them are applicable. Some of these use cases you have presented. I mean, we know there are existing techniques, right, for this, the statistical, multivariate statistical analysis tools and so on that have always been there. And now with the federated learning, aren't we like creating more trouble than we can actually handle with this thing? Or what is your opinion? Because it seems like actually some of these robust methods for secure aggregation are based or are somehow devised from the from this kind of distance metrics as calculating a centroid and seeing the residual distance to the to the actual linear regression for acceptable points. And on the other hand, if you want to personalize things, perhaps users in their apps or unseen data that you want to incorporate into the model, it's going to have actually a higher distance, a longer distance than you might expect in this sort of classical outlier detection methods. So it's kind of like follow the majority kind of regression thing, or else be discarded. So it's kind of hard. I just wanted to point out that there is this personalized federated learning approach that I haven't looked at in detail, but is that what you are doing actually in this federated learning use case you were presenting? Or if I understand, or is it just about securing like the architecture concept that you are using?
So I would say the work we have been doing, it's not specifically tailored to a given model or technique. What we wanted to provide is something which enables different application or different providers to train jointly in a federated learning fashion their data, rather than doing that in a silo. So in that sense, that can be applied to any area where federated learning or personalized federated learning can be applied. So that was what federated learning as a service is. It's not tailored to a given model or to a given approach, but can be applied to extended to other. And the second one was, the privacy PPFL. That is was more on securing the models from the attacks, looking at the gradient, which was an emerging trend of attacks that was happening there. So that so we were not looking specifically to this personalized model itself. Then now, yeah. So I agree with you on this on the fact that there is this different technique, and sometimes doing federated learning can bring the local model far away, or can you do personalization. I think that both are supported by the tool that we are looking at. And I was saying earlier, I think that personalization can often help the local model to be more tuned. Now that gets more complicated when you look at anomalies, because then you would have to personalize anomalies. So there are interesting questions and approaches in this personalization and of local models, which I think it's worth looking at. That our techniques don't specify any of those, but can be able to support both. But there is an interesting aspect to look into that. Also, there's been a lot of interesting work besides federated learning on transfer learning. So you try to build a model in a given context, try to apply that to another context, and very often this fails, especially when you look at network, because of the specific characteristic of the networks. There are some of these one-shot approaches where you're trying to learn just from first shots, getting the knowledge from a previous knowledge, which I think those are interesting and a bit less explored, at least for networking context, at least from what I've seen, what I've observed.
Okay, thank you.
So thank you, Alvaro, for your question. Well, so I think we can close it here today. Thank you again, Diego, for your talk and your nice presentation. Well, and it was a pleasure having you here in our seminars. Hopefully we see you soon in Madrid.
Great, thank you very much for inviting me, and feel free to reach me out if you have any further questions or interest topic for collaborating. Thanks.
Thank you.
Bye.